Okay, so as promised, here's the explanation to question number 3 on page 21 of your packet. The scenario is about a baseball player sliding into a base. Just note that if you hear any weird sounds, I happen to be filming this while the haunted house is going on immediately downstairs from me. Let's walk through this scenario though. Okay, so at the moment that a player is sliding into the base, I'm going to make the assumption that the player is touching the base. You could assume differently and not include the base in the problem, and I don't think there'd be any significant differences here. Let's begin with the system schema. Please start by labeling the baseball player at the center. Every object gets a solid outline. The object of interest, or the center of our system, should get a dashed outline as well. Other objects in this scenario. So this is going to be highly dependent on the individual scenario. The earth is involved, the ground is involved, and I'm going to include the base as well. I'm going to exclude air, as in air resistance, because I think in this scenario, the baseball player is moving at such a low speed that there'd be negligible air resistance. These are the objects with which the baseball player interacts. Connect each of them and identify each of those with a force name. The earth player interaction is known as the force of gravity. The player-ground interaction, actually interactions, there's 2 of them. First of all, there is the normal force. The ground is supporting the player. The second one is friction. As the player slides into the base, their motion is being resisted by friction. And then finally, the base itself. As the player slides into the base, it's a small effect, but the base does push back on the player. I'm going to call that an applied force for lack of any better or specific of a name. One note. These interaction arrows all need to have an arrow on both ends. The reason is, you've heard of the idea of for every action there's an equal and opposite reaction. Well, that's what's going on here. As the player interacts with the base, so the base interacts with the player. That reaction is equal and opposite. So the force applied by the player on the base is the same magnitude or size as the base on the player. That's why we put a double arrow there. That's what we're trying to represent. I believe that I've included all the interactions here, so I'm going to move on. What do I mean by sign conventions? Sign conventions, this is probably going to be the same in every scenario on this page. To the right, I typically consider that direction positive X. And up, I conventionally assume that that's positive Y. It turns out you can actually choose what you want those to be in any given problem. That's why it's handy to state them as you start working on the problem. So when I think about the player, I want to consider how the forces add up. Think about it first in terms of motion. In the vertical direction, the player is not really moving at all. In fact, I'm going to say that the amount they move vertically is negligible. If you're not moving at all, you have a 0 velocity. If your velocity is 0, it's also constant. Sum of the forces in the y direction has to be 0. In the horizontal direction, this entire scenario depends on the fact that the player's slowing down. So I need to have a net force here. So let's just take a moment and consider that in the picture on your page, the player's sliding from right to left. They're actually sliding, they're moving in the negative direction. This means that the sum of the forces in the x direction is positive. I.e. opposite the direction of the player's moving. When you have a motion in one direction and a net force in the other direction, remember that's going to slow you down. This I'm going to fill in as we go, subscripts. You'll see why here in a moment. Here's the ground. Here's a simplified version of the player. Okay, when writing out fully subscripted forces on a force diagram, refer to the key, the legend at the top of the page in this section. I want you to fully write these out, at least to begin with. This is so that we can make sure you really identify where these forces are coming from. The gravitational force on the player is exerted by the Earth on the player. Now's where these abbreviations come in. E for Earth, P for player. Okay, the player, just a reminder, is moving that way. Let me add that in here somewhere just so that we get a note of that. Just a little note off to the side that the motion is in this direction. With the motion in that direction, this frictional force that I identified here needs to go opposite that. Now, if I consult my system schema and my force diagram, I need to make sure I've accounted for all the forces. FG, FG, FF, FF, N, FN. Okay, I haven't yet put down the applied force between the base and the player. So when the player's coming into the base is pushing back on the player. All four interactions here are now shown here, and it's now very clear, a quick check of my work. I said that the sum of the forces in the x direction would be positive, which is also meaning to the right. When you look at this picture, there are no leftward forces, all the forces to the right. This checks out. Vertically, I said that the sum of the forces would be 0. My two vertical forces, therefore, I should make every effort to try and show them to be equal in magnitude, make the lengths about the same. So if I want to be a little more careful, I might extend that line. So this is a complete version of number 3 in your packet, page 21. Hope that's been helpful. Feel free to drop me any questions by email.